Hi everyone. So we are still working on atmospheric stability using environmental lapse rates on soundings. And we are finally to unstable atmospheres, which are the most exciting of all. And we're going to do a quick intro into unstable atmospheres using soundings and environmental lapse rates. And because you've done so much work on other things, you can go through this quickly and get right to cloud base and cloud temperatures next. Let's look at unstable atmospheres. When we think about unstable, we observe things like clouds where the top seems to explode past the anvil. Remember, the anvil is literally the lid of the warmer air in the stratosphere that is preventing this parcel from moving up anymore because there's the parcel can't become less dense. It is now cooler than the stratosphere above it. But in the center of these storms in the column, there is so much energy from the latent energy release that this central column can maintain its warmth and break through into the stratosphere. That is an unstable atmosphere hallmark. And you might see it, since you're not at stratospheric levels, you might see it look like this from underneath. And if you were in a Hurricane Hunter plane, you might see an anvil like this at the stratospheric level, and then here's the breakthrough right there where the central column is pushing up and exploding through the stratosphere. The hallmarks of an unstable atmosphere, a cumulonimbus cloud that has broken through the stratosphere. Here is a situation that is more normal for you to see in a unstable atmosphere that is not quite so dramatic, and we'll explain the differences in a second. But you might see a plume of smoke from a smokestack that is not taking that horizontal route through a stable atmosphere. Instead, it is ascending, and that climb, that rise, is like the rise that you're seeing here. It's the same situation. This does have updrafts and dramatic downdrafts, just like the plume will have a dramatic downdraft farther out and away from the smokestack. So these do have an equilibrium. Unstable atmospheres do have an equilibrium of updrafts and downdrafts. The downdrafts can be fierce, and they are often farther away from the central column. So unstable atmospheres really develop during the afternoon, and they develop in the afternoon from that average environmental lapse rate, which is on that moderate slope that we're used to. And what happens in the afternoon is that the ground is warming intensely and absorbing more radiant energy than it is emitting, because there's so much radiant energy coming in from noon till about 3 or 4 o'clock. So the ground is warming intensely. It can't emit off everything right at that moment. It will emit it off overnight. And as a result of that relative lack of emissions, the atmosphere above is relatively cooler than the very hot ground. I'll give you an example. I'm an EMT who covers half marathons, and half marathons are often during the summer months, and I will have patients who will go down with heat stroke, and the first thing I do is to take off their shoes and take off their socks and coat their feet with cool water and cool towels. The reason for this is I know that the ground within the first few inches, first 6 inches or so, is 20 to 30 degrees Fahrenheit hotter than the ground that is up by their chest and their head. So that ground that is 20 to 30 degrees Fahrenheit hotter is making their feet so hot that that's the place where I can really resolve the heat stroke fastest. The same thing happens here. The warm ground heats dramatically, and relatively a few hundred meters up is relatively cool. That difference allows parcels coming off the ground to really rise dramatically because they are so much warmer than the atmosphere around them. So that's what you need to remember. The ground warms dramatically, the atmosphere is still cool. Some parcels can convect up and release latent energy with condensation, stay relatively warmer than the cool atmosphere, and continue rising up. That's the hallmark for an absolutely unstable atmosphere. When we take those observations and when we take that data, we can look at more data and do some calculations. And here's where we look on the same sounding that we've been looking at. We have seen in this sounding from the ground up, we've seen force lifting, we've seen an inversion, we've seen an isothermal section, we've seen a conditionally unstable section, and now the rest of this is actually showing an unstable atmosphere. And we know that by doing the calculation for our observation. And our lapse rate here is 9 degrees Celsius, which is greater than the 3 to 8 degrees Celsius drop per 1,000 meters that we were seeing at conditional instability. When we're looking at a lapse rate of 9 degrees Celsius, a higher lapse rate, here's where we're getting it. We can look at an area like this, 7,600 meters up to 8,580 meters, which is practically 8,600 meters. So about 1,000 meters difference between these two data points. To find the temperatures for those two data points, we extrapolate down to the x-axis. And at this initial data point, we get to a temperature of approximately negative 18 degrees Celsius. And then when we come up here to the later data point and extrapolate down, we come down to an approximate temperature of negative 27 degrees Celsius. We subtract the later temperature from the earlier temperature. In doing so, here's our equation. Negative 18 minus negative 27 degrees Celsius. That means subtracting a negative number is adding that number. Negative 18 plus 27 degrees Celsius equals a lapse rate of 9 degrees Celsius per 1,000 meters. That is a higher lapse rate. That falls into the category of absolutely unstable atmospheres. When we look at that category, think of unstoppable movement or vertical movement of the atmosphere. Think of unstoppable vertical movement and unstable atmospheres. I hope that that mnemonic will help you out a bit. And in fact, when we look at a generalized view of atmospheres, we see that this entire area, which is a lapse rate of greater than 8 degrees Celsius per 1,000 meters, 9 degrees Celsius, 10 degrees Celsius, even 11 degrees Celsius drop per 1,000 meters, falls into the absolutely unstable range when we see it on a sounding. Last but not least, our lapse rate is the change in temperature, which is change of x, over change of altitude, which is change of y. This is different from slope. We've reversed it and it's different from slope. It is a lapse rate that works because it utilizes the y-axis for altitude. It is not so much an algebra mathematical construct as it is a logical and scientific construct for the atmosphere. So again, lapse rates are change in x-axis over change in y, change in temperature over change in altitude. Absolutely stable atmospheres feature high lapse rates of greater than 8 degrees Celsius per 1,000 meters. See you on the next video.